Okay, so welcome everyone. This is the very last One World seminar for the Christmas break. So we're very happy to have Anna give this talk. So Anna got a PhD from Duke University with Mauro Maggioni. She was an assistant professor at Jacksonville University and then the postdoc at Michigan State University, and she's currently tenure track at University of Utah. So we're very happy to have her, and she's going to be talking about unbiasing procedures for scale-invariant multi-reference alignment. So thanks, over to you.
All right, thank you so much for the invitation. It's a real pleasure to be here. And thank you all for coming on this. I know it's the end of the semester and it's finals week for us, and I know everybody has a lot on their plate right now, but it's great to be here and thanks for coming. Okay, so I am going to be talking today about multi-reference alignment problems. First, I'd just like to acknowledge my collaborators on these projects. First of all, Matthew Hearn, formerly at Michigan State. He's actually at Citadel now, so no longer at Michigan State, but we worked together on this when I was there. Cooper Bonis, who's a postdoc here at University of Utah, and also Liping Ying, who is a graduate student at MSU. Okay, so I have a little outline planned for today. We'll see if I get through all of it. If not, I'll skip the last part, but I'll start with a little introduction to multi-reference alignment. Why do we care about these problems, and some different relevant data models to think about. And then I'll talk a little bit about one approach for solving these problems, which is differential unbiasing with wavelet invariants. So talk a little bit about these wavelet-based features and advantages and disadvantages. And then I'll talk about an alternate method for solving this problem that we developed, which we call inversion unbiasing. And the basic idea being that if you have more information about the noise, you can build something smarter that gives better results. And then finally, time permitting, I'll discuss a little bit how to recast multi-reference alignment as a distribution learning problem where you have bias scale batches. Okay, so the motivation for studying these kinds of problems arises in many applications. One of the main ones is cryo-electron microscopy, or cryo-EM. And so this is a very important, well, a technology that's gotten a lot of attention recently. It won the Nobel Prize in Chemistry in 2017. And the basic idea is that so it's molecular imaging, and you have molecules which are frozen in a protein sample, and then you shoot them with an electron beam, and then you have a little electron detector on the other side, which takes a picture essentially takes a picture of the molecules. But this is it's created a lot of data, and it's a very challenging application for a number of reasons. First of all, there's lots of measurement noise, so you may have these sorts of three-dimensional shapes in your microscope, but the actual images coming out of the microscope are highly grainy, sometimes so much so that you can't really see the individual structures very well. So you're dealing with a very low signal to noise ratio. And then secondly, these molecules can be in any configuration. So they can be rotated upside down or to the side. So for example, if you have, okay, this is a fake molecule, but you have like this little Mickey Mouse molecule, depending on how it's rotated, the pictures of it that you actually see from the microscope could look like any of these pictures below. And so somehow you would want to aggregate all of those different images together to reconstruct this 3D approximation of the molecule. And then another thing that can be quite challenging is deformations that occur in the molecules. So for example, if you take this picture here on the right side, some molecules have flexible regions which tend to kind of flop around. So depending on which configuration it was in when it was frozen, you have additional variations in addition to the rotations that are from the different positions that it could be in. Okay, so there's many challenges to this application. Kind of the unifying theme of what I'll be talking about today, though, the basic setup of interest is we're given a large number of noisy observations of a target image or signal. And then from that large number of noisy observations, we want to recover a high resolution approximation of the target. So the target can't be observed directly, only noisy versions, and from the noisy versions, we want to recover the target. Here, I'm being very loose with what I mean by noise. So noise can mean many things, and in particular, I'm going to be thinking about additive noise, random translations, random rescalings. I won't be talking about rotations today, but that's another important one to think about. Okay, so sort of a starting point for these really hard problems is to start simple and build up. So one of the most basic toy models for considering these kind of problems is known as the 1D multi-reference alignment, or MRA model. And so the basic setup here is you have a hidden signal F. This is the target that you're trying to learn. And you don't observe it directly. What you observe is you observe this signal, which has been randomly translated by some shift t, and then corrupted by epsilon. Epsilon here is Gaussian noise. And then you observe y, but you get to observe it many times. So we'll assume we have a sample size of m. And the goal is to recover the hidden signal from all of the noisy y's. Okay, so the MRA model thus really includes, kind of two underlying noises or sources of corruption. First of all, the random translation, and then the additive noise. So these epsilons are independent white noise processes with a variance of sigma squared. So sigma squared, the larger the sigma, the higher the noise in the data. Okay, so one of the models that I've focused on has been a generalization of this, most classic model to include random rescalings, which is important in a number of applications. So one of the models I've worked on is the following, which I'll refer to as the generalized MRA model. So here we have, we think of this L tau as a dilation operator. So L tau acts on a signal F by an L1 normalized dilation by a factor of 1 minus tau. And we consider the more general MRA model where you start with a hidden signal F, then you randomly translate the signal by some shift T, then you randomly dilate, or you could dilate first then shift, doesn't matter, but you have a random shift, you have a random dilation, and then on top of all that, you have lots of additive noise. Okay, and then the eta squared here I'll use to denote the variance of the taus of these dilation factors. So the larger the eta, the more rescalings you have going on in your data, and sigma here will continue to denote the additive noise. Okay, so here's just a little picture, a little model illustration. So we have some hidden signal that we're trying to learn. That's going to be one of these blue curves right here. And so first of all, this blue curve is randomly translated, like you see in the first column. Then it's randomly dilated, like you see in the second column. And then you have additive noise on top of that, which could be, if it's a small amount of additive noise, you might still be able to detect, where the peak of the signal is. But if it's a very large amount of additive noise, you're going to be observing something more like this last column, like these purple curves. And from a large collection of these purple curves, you want to aggregate all that information together, and you want to recover one of the blue curves. Okay, here's a little illustration of what this model is in 2 dimensions, even though I won't be talking about the math for the 2-dimensional case. It actually would be very similar. This is what the model would look like. You have some image that you want to recover, but you don't observe it directly. Instead, you might have these other noisy cat images, and you might have the image at different amounts of zoom, and then you might have a lot of noise on each image, and you want to put all the noisy images together to recover a nice picture of the cat. And I should say, please interrupt with questions anytime along the way. I'm happy to stop and do questions along the way. Okay, so so a little motivation. Why do we consider this model? Why think about dilations? Basically, we want to analyze the effect of a deformation on the signal input. So if the input to some function is deformed, what's the result? So we could, as this is modeled by some operator acting on the signal. I'll use like a tau tilde here to kind of say this is different than the tau that we had previously. But this is just, this deformation is f evaluated at tau tilde of x. So instead of inputting x, we're inputting some deformation of x. And there's essentially 2 ways to go if we want to recover things. The first option is to assume that this deformation is small in some way of measuring size. It's, maybe close to the identity, or it has a derivative which is small. But the other option is, not to assume that it's small, but assume that it acts according to a known family of group actions. If you know what those group actions are, then you can build more targeted methods for dealing with them. So we're going to be thinking about this second approach, and in particular, considering dilations and translations of the input. And this corresponds to basically the simplest case of diffeomorphisms that you can consider, which are linear diffeomorphisms. But we'll see that even this linear case is quite challenging, and it took us a bit of time thinking about it to develop what we've gotten so far. Okay, so what approaches are out there for the classic problem? I'll review these briefly and then discuss, the sort of how we can build on them, but why they're not quite enough for the generalization. So there are various approaches for solving the classic problem. First of all, synchronization. The idea here is that you first want to align the signals, maybe like line up all the peaks, and then average out the noise. But this is going to fail in the low SNR regime. For example, remember those purple curves, there's no way that we could align them. There's just no way to tell. Another approach is the method of moments. The idea here is that we want to recover this hidden signal f from various statistics on the noisy signal, for example, the mean, so the expected value of the noisy signal and the covariance of the noisy signal. And then a special case of the method of moments is the method of invariance, where you recover f from translation invariant features, i.e. Fourier invariance. And so this is kind of the approach that I will be kind of generalizing or talking a lot about, this invariant-based approach, which is really useful in a lot of cases. You can also go, very different route, which is not building invariant representations, but more algorithmic expectation maximization algorithms. And these tend to give good results, but they are expensive. So you do run into some issues with scalability to large data, and getting stuck in local maximum. Okay, so for the Fourier invariance, so one approach then for solving this classic MRA problem when you don't have the dilations is to use the following features, all of which are translation invariant. So the simplest thing you could look at is just the integral of y, right? So the mean, and that is certainly translation invariant. Sort of the next simplest thing you could think about is probably the power spectrum of the noisy signal. So Py is defined as the square of the magnitude of the Fourier transform of y. And you can check that, you know, a translation just affects the Fourier transform, just affects the phase of the Fourier transform. And so when you take that modulus, it kills the effect. And then the third thing that you are sort of the next most complicated thing you might think about is known as the bispectrum. And this is also computed from the Fourier transform. You have y hat of omega 1, y hat of omega 2 conjugate, and then y hat of omega 2 minus omega 1. So it's based on the Fourier transform, and it's put together in such a way that all of the phase factors arriving from a translation perfectly cancel each other out. Okay. So these are all translation invariant features which can be used to recover the hidden signal in the classic case, but they won't be sufficient, or they're not going to work for the generalized MRA model, because the dilations will cause large perturbations in the frequencies, especially for a high frequency signal, and the representation won't be close to what it is for the true signal. So we need to either compute, I guess, again, there's kind of two approaches you could go. You could compute a translation and dilation invariant representation. Then you kind of worry you've lost too much information and it won't be invertible anymore. Or you can remove the dilation bias from the translation invariant features. Okay, so there's some sort of choices that go on as you're dealing with these kind of problems. What kind of representation are you going to use to try to recover the hidden signal? There are a lot of things that you want. You probably won't get all of them, but what would you like? So here's a little wish list of what you would like in choosing a representation. First of all, you would like for it to be translation invariant. That's probably somewhat non-negotiable. And then secondly, you would like for it to be complete. So if, you know, the representation of F matches the representation of G, then you really want these two signals, F and G, to be the same signal up to a translation. So you want this representation to uniquely define the signal up to translation. And we'd like for it to have a known bias. Otherwise, we can't define an unbiased estimator for the representation. And then finally, and a very important point, we want it to be not just mathematically invertible, but numerically invertible. We want a tractable algorithm for recovering the hidden signal from its representation. Okay, so one way to go is utilizing wavelets for wavelet-based representation, wavelet invariants. So here's just a little recap of the wavelet transform. So to compute a wavelet transform, you start with psi, some mother wavelet, which usually you assume has norm 1, and then you create a whole family of these wavelets by dilating the mother wavelet. So psi lambda will be the mother wavelet dilated by a factor of lambda. And then you define a wavelet transform, WF, acting on a signal F, as F convolved with psi lambda. So what's the idea? The idea here is that as you increase lambda, the wavelet oscillates more rapidly. So the frequency of that wavelet increases as we increase the lambda. And if we look in the Fourier domain, what is happening to the support of the Fourier transform, it's shifting higher and higher into the high frequencies. Okay. Okay, so so one thing that you can do is define the following nonlinear wavelet invariants at frequency lambda. So I'm going to use S for the wavelet invariance. So SF is the wavelet invariance of the signal F, and these are going to be a function of frequency. So these wavelet invariants at frequency lambda will simply be the 2 norms squared of F convolved with psi lambda. And if you want to think about what is that doing in the Fourier domain, so here you have the power spectrum of F, but you're kind of like zooming in on a certain band of it, right? So psi lambda is going to zoom in on a certain band of that power spectrum and aggregate that information together. So not just, you know, so this is going to tell you frequency information at frequency lambda. And the natural thing we would want to compare this to in terms of pros and cons of these 2 representations would be just the power spectrum of a signal. So I'll call that PF, like I did on the previous slide. Okay, so so these wavelet invariants are in fact the first layer in a non-windowed wavelet scattering transform. So this non-windowed wavelet scattering transform was introduced by Milan in 2012. And the idea was to sort of harness the power of convolutional neural networks, but with sort of predefined, pre-selected filters, allowing you to prove explicit stability guarantees. And the basic idea is, you know, as in a neural network, you have a cascade of convolution and nonlinearity, convolution, nonlinearity. And so here, there's you can also, there's various variations on this theme, but one can think about just sort of reading off the norms, the LP norms of these things. So here we would be at the first layer of the L2 norm of F convolved with psi lambda. Okay, but this is just sort of to put it in context. We actually don't go deeper into these transforms, but there is a connection with this. Okay, so in terms of comparing these 2 representations, these wavelet invariants and the power spectrum, you can actually prove that for suitable mother wavelet and general signals F and G, that their power spectra will equal if and only if their wavelet invariants equal. So these wavelet invariants really are containing all of the information of the power spectrum. So the punchline here is that this wavelet invariant representation, it's not invertible for all signals because, well, it's computed from the power spectrum. We've thrown away the phase information, and that's generally quite important for recovering the signal. But if we know these features, if we know these wavelet invariants, then it's equivalent to a phase retrieval problem. We essentially reduce it to a phase retrieval problem in which we know the power spectrum. And in terms of computation, you can solve a convex optimization problem. So once you have recovered the wavelet invariants, you can feed into a convex optimization problem and turn that into an approximation of the power spectrum. And you can get back that power spectrum representation if you like. Okay, so here are some results for the classic MRA model. And these are essentially generalization of results that are already known in the literature for the classic model, and just saying, yeah, same thing still holds for the wavelet invariants. So what's the idea? So I'm going to use this bar here to denote an empirical mean. So PY bar is just the empirical mean of the noisy power spectra. And similarly for For SY bar, this is just the empirical mean of the noisy wavelet invariance. So you can actually show if you define an estimator of the power spectrum as here. So this PF tilde is going to denote an estimator. So we have an estimator which of the true F, of the power spectrum of the true F, which we get from the noisy power spectra with some minus sigma squared, a little additive noise unbiasing. And we can do the same thing to get an estimator for the wavelet invariance. And we can prove that the error of these estimators is upper bounded in the following way, right? So the most important thing here is this square root of m, and the denominator. In both cases, you're getting a nice convergence of this estimator to the true thing. Okay, so a couple of comments, some of which I probably already said on the previous slide, but we obtain unbiased estimators. So for both the power spectrum and for the wavelet invariance, this simple estimator converges to the representation of the true signal as m goes to infinity, and then biasing procedure is simple and linear. Okay, so some observations though for the generalized MRA case. Like I said, these random dilations cause large perturbations in the high frequencies, and so these classic approaches are not going to work, are not going to be sufficient in this case. So one thing that you can do is to apply a differential operator to the empirical mean to essentially unbias for the effect of the dilations, to adjust it a bit for the dilations. This is how you do that. This is, I'll call this our differential unbiasing for generalized MRA. And it looks a bit messy, but it's actually rather straightforward. So we have this order K wavelength invariant estimator. And what's it going to do? Well, right, it's going to start with the empirical mean, because that's really the only thing you have access to. You just have access to this noisy data. But then this is extremely biased. So what you're going to do is adjust this empirical mean by subtracting off some derivative terms, right? So we're going to take it, we're going to subtract off, a second derivative term, where we have some constants, and also depending on the variance of the dilation distribution, and up through the kth even derivative. Okay, so we're just adjusting the empirical mean, utilizing the first k/2 even derivatives and sigma squared, the additive noise variance, eta squared, the dilation variance, and some constants depending on the dilation moments. And I probably should have put this on the slides, but I didn't. But there, you can easily sort of see why you would want to do something like this if you think about, okay, I have a signal which is dilated by tau, and I look at what happens to the wavelet invariance. I do a Taylor series expansion in the dilation variable, and then take expectations and sort of see how it behaves. So it's based off of a Taylor series expansion in the dilation variable.
And can I ask a quick question?
Yeah, absolutely.
These constants B, are they kind of known, or are they sort of,
Yeah, great question. So we are assuming that they're known, but of course, in practice, they might not be, and you would have to figure them out. So of course, that's a great question. In general, they are, in general, we're sort of thinking that somehow you have at least this much information about the distribution. In practice, you'd really need to think about how to figure it out. But it is harder. Well, it's a lot harder than I originally expected. Somehow I thought even just figuring out what the eta squared is, when you have random translations, random dilations, and additive noise, when you have all three happening at the same time, it's actually quite difficult, and we haven't thought of a good solution to that. If you have ideas, I'd love to hear them. So this is one, yeah, so that actually it's a good comment to make. That's a hard problem that we have not solved. So if people have ideas on that, I would love to hear it. Yeah, if you have any two, it's easy. So like any two of those three corruptions, it becomes easy. Other questions while we're doing a little question break?
If people want to put questions into the chat as well, I'm quite happy to read them out. Should have said that from the start.
Okay. So then what we were able to prove is that with this, unbiasing procedure based off of the derivatives of the representation, you can upper bound the error in the following way. You have, two terms right here. You have one here, eta to the k plus 2, depending on the dilation variance, and then another term over here, which we're not so worried about because of this square root of n. Okay, so the error depends on the sample size, on the unbiasing order, and of course, importantly, on the additive noise variance and the dilation variance. Okay, so basically, the error consists of two parts. A variance term, which decays to 0, like 1 over the square root of n. So that's nice, but unfortunately, you also have this bias term. You have this, constant times eta to the k plus 2. And the unbiasing procedure has helped. It's essentially reduced the bias from eta squared to eta to the k plus 2. But unfortunately, you're always stuck with some bias. And you can't take k too large. You might want to just take k to infinity and send that bias to 0. But unfortunately, the constant in front of it also grows rapidly in k. And after a certain point, it doesn't help to increase the k. So you will always be stuck with some bias in the representation. However, it still is helping a good bit in many instances. So for example, let's say you have the following high frequency signal f, and then this is showing the error decay for approximating the power spectrum of this signal. So the blue curve is kind of like the baseline, because that's just the error decay that you get without any unbiasing for dilations, just with additive noise unbiasing. And then the red, orange, and yellow curves are the error that you get using this wavelet invariant approach. And in particular, the orange and the yellow are utilizing the unbiasing procedure. And you can see it is significantly reducing the error, which is nice. But at the same time, you do see like it plateau, kind of have this nice linear decay till it hits a certain point and then it plateaus. So that's sort of illustrating the bias. And then here's a little sort of also illustration of the signal recovery. So in general, these features are not going to be sufficient to recover the underlying signal, but there are a few special cases where the power spectrum is invertible. And this is one of those special cases. It's not true in general, but it's a good little illustration. So maybe starting off in this last figure here, the purple curve is the power spectrum of the hidden signal. So that's what we would like to obtain, the purple curve. What do we actually observe? We observe the blue. So you can see that this is the empirical mean of the noisy power spectra. You can see it's really like flattened because of the dilations. And the unbiasing procedure that we're proposing sort of starts with this blue curve, and it pushes it up to the red, which you can see is a lot closer to the purple. And then the corresponding pictures, if you go back to what the signal looks like, here's the target signal that we're trying to learn, and then here's the red one, which we recover with these wavelet invariants. And so it's certainly not perfect, but it's pretty close. And the blue one is what you would get if you did not do the unbiasing procedure at all. So you see how much the dilations are affecting the signal recovery. Okay, so all right, so in the next part of the talk, I'd like to sort of, think about the advantages and disadvantages of what I just told you about, and think about another approach that we could possibly do. So the advantage of the previous approach is minimal assumptions on distribution of dilations. We're only assuming knowledge of the first few moments. Granted, even that might be difficult to obtain in practice. But we also had some significant disadvantages. We did see that we're always stuck with some bias, that it was impossible to obtain an unbiased estimator. And that secondly, I guess I didn't really illustrate this a lot, but we did observe this, that even though PF and SF are mathematically equivalent, the actual numerical procedure for recovering the power spectrum from the wavelet invariance is a bit unstable. So it's essentially driven by the smallest singular value in a low rank matrix, and so it's not great numerically. So we sort of took a step back and thought, okay, we were not able quite to solve the problem in the way that we wanted. What if is it even possible? So is it even possible to have an unbiased estimator in this case? Let's first of all take like the simplest thing that we can. Let's assume that we know explicitly the dilation distribution. And then let's also think that we have as many samples as we want. So we'll think about like an infinite sample size. And in this special case, is it possible? So for simplicity, let's assume that the dilation distribution has an explicit form, and that we know that it's uniformly distributed. Okay, so actually, if you have that additional knowledge, you can do so much better. So here is a result showing that what do we have? That you can perfectly recover the power spectrum of the hidden signal F with the following approach. You take if you have the expected value of the noisy power spectra, so this is available in the infinite sample limit, and you also add on this derivative term and subtract off the additive noise. And then you apply the inverse of an operator L, which is the difference of two dilation operators. This actually, maybe somewhat magically, perfectly recovers the power spectrum of the hidden signal. And the idea is that, we have access to this expectation of the noisy power spectra as m goes to infinity. In the infinite sample case, we get perfect recovery. Probably in the finite sample case, we can approximate that thing pretty well and still get an unbiased estimator. So that's the question that we ask. Can we generalize this to the finite sample case? And you certainly can. So the answer is definitely yes. And you can approximate this term that you need and also its derivative just by looking at the empirical, the mean of the noisy empirical power spectra and smoothing it out with a little Gaussian filter. But that's all that's really needed. And so at the end of the day, you take your mean, you smooth it out, and you first of all compute this term from the data, and then you apply this inverse operator, which is known because of knowledge of the dilation distribution. And then you can prove that the mean squared error of this estimator is upper bounded. Maybe just take a look at the bottom of the slide. So if you choose the width of this Gaussian filter in the right way, then in a way to kind of minimize this bound, then you get an error, a mean squared error, which is like eta squared over m plus sigma to the 4th over n to the 2/3. Okay, so we were quite pleased with this because now we have an error decaying to 0 at a nice rate. And we've also defined this directly on the power spectrum to avoid the unstable inversion. Okay, so we get an unbiased power spectrum estimator with a mean squared error like 1 over m to the 2/3. And let me just say, I think I'm going to skip over some of this because I think I'm going slower than I expected. But in terms of actually inverting that operator, you have a closed form formula for L, but you don't have a closed form formula for the inverse. But the estimator is easy to compute by solving a convex optimization problem. And so that's actually straightforward, and that optimization works quite well and is quite stable. Okay, so just to kind of illustrate the point here, this is another, kind of medium frequency signal. The purple, here I'm once again showing the power spectrum. So the purple curve, which is in the very back, that's the power spectrum of the true signal. What you actually observe is the blue, right? This is the mean of the power spectra from all the dilations. It's again like quite flattened and quite far from the truth. And then this inversion unbiasing procedure takes the blue curve, pushes it back up to the purple. And in this is a regime of actually much larger dilations. So the eta here is a lot larger than it was in the example I showed you before. And the differential unbiasing procedure is breaking down because it's essentially based on an assumption that the eta, that you can Taylor expand these things and the dilation factors aren't too large. And then in terms of the signal recovery, for the example on the previous slide, again, this is a special case where you can do this. You can't normally do this, but here's the target signal in purple. In red, the one we recover with the inversion unbiasing. The first approach is failing because the dilations got too large. And then this blue one is what you would recover just from the power spectrum without any unbiasing. And you can see how corrupted it is from the target. Okay, just error decay plots showing that these things decay, nice linear decay without plateauing, right? So compared to what we had before where we see this plateau, we continue the error decay of this estimator is in red, and you'll see that it's a nice linear decay in all the cases. Okay, so I've talked a lot about recovering the power spectrum of the hidden signal. Of course, that's not fully solving the problem because what we really want to do is fully recover the signal. And in general, the power spectrum is not invertible. So can we extend this procedure to operate on higher order invertible Fourier invariants, which, yes, which are invertible? So the answer is yes. And first of all, what do I mean by higher order Fourier invariants? So far, we've been talking about the power spectrum, and the power spectrum is just the Fourier transform of the second order autocorrelation function. So if you have, define this autocorrelation function, take the Fourier transform, you get the power spectrum. You could define higher order autocorrelation functions. For example, this triple correlation function A3 can be defined by integrating y, and then y shifted by t1 and y shifted by t2. And if you take the Fourier transform of this function, you get the bispectrum. So you get a translation invariant, that translation invariant representation that I mentioned in the beginning of the talk. And this is actually a general principle. By taking the Fourier transform of the nth order autocorrelation function, one obtains nth order Fourier invariance. And so you get essentially a principled way of obtaining increasingly expressive translation invariant features. You can apply really this unbiasing procedure on any order for Fourier invariance. So the observation is as follows. If your signal is dilated, then the higher order Fourier invariants are only affected in the radial variable. So as long as you sort of remember your polar coordinates, it actually becomes quite simple. You simply write, the expected value of these Fourier invariants and polar coordinates, apply inversion unbiasing in the radial variable, and then invert the representation. And you can prove basically the same result that I showed you for the power spectrum. You can prove that for the bispectrum. So here's an estimator of the bispectrum of the hidden signal, which is defined in a very similar way to what we had for the power spectrum. And you can show that the mean squared error for this bispectrum estimator is now upper bounded as follows. Again, we have eta squared over m plus sigma to the 6 over m to the 2/3. It's identical to what we had before, except this sigma to the 4th now becomes sigma to the 6th because the bispectrum has a term which is cubic in the noise. So that's unavoidable. Okay, and here's like a little picture illustrating how the unbiasing behaves on the bispectrum. So first of all, on the left, you see the ground truth. So this is the true bispectrum of the hidden signal, but we don't observe this. What we observe is here in the middle. So after we average all of the dilated versions of the bispectra, we obtain this picture right here. And you notice like the support, it's like completely distinct from the original one. But we can apply this same unbiasing procedure and essentially like push out this representation. And this last figure is what we recover, which you see is quite close to the bispectrum, the ground truth bispectrum. Okay, so when the dilation distribution is uniform, we can reduce the problem to inverting the bispectrum. And the bispectrum is invertible under fairly general conditions. So that's the good news. And there are a number of algorithms which are options for doing this. For example, non-convex optimization over the manifold of phases, iterative phase synchronization, frequency marching, tensor decomposition algorithms, a number of options. Okay, so as we're sort of running low on time, I'll probably start to wrap up just telling you about some of the future directions that we're thinking about related to this. So first of all, what about other dilation distributions? So I got some really nice results for the uniform distribution, but you may wonder, is there something special about the uniform distribution? Can you generalize? We expect, indeed, that to be the case, that there's a more general principle at play, but it's based on not explicit knowledge of the dilation distribution. So if you know it, whatever it is, you can, define an operator, which is, the integral of dilations times the derivative of the dilation distribution, and then the power spectrum or higher order feature is recoverable from from, first of all, an input, which you can approximate from your data, and then an operator, which you can compute given knowledge of the dilation distribution. Okay, so when that distribution is known, we expect we can unbias the Fourier invariance by inverting this operator. Okay, so of course, this sort of big open question then becomes, when it's unknown, can you learn that dilation distribution? How can we learn the dilation distribution? Like I sort of hinted at earlier in the talk, this was a lot harder. Even learning the moments was a lot harder than we originally anticipated. So this is, sort of a really important question if these methods are to become applicable for real data applications. And we've had some ideas. We haven't quite worked it out yet, but one idea is to, again, utilize the wavelet invariance at, sort of at a dyadic scale to what I had before. But if you sort of change the scale, then what actually happens is that in this representation, in this wavelet variant representation, dilations show up as translations. So one idea is that you could first compute these wavelet invariants and the dilations become a translation. Then you could compute like a translation invariant representation, like the bispectrum or something like that, to recover the full thing. So this would involve, probably both solving a non-Gaussian classic MRA problem and then trying to learn this distribution by solving a deconvolution problem. Right. So this is one approach that we're interested in. Another thing that we're interested in is sort of recasting MRA as a distribution learning problem. So I'm actually very interested in this, but I ran out of time to talk about it. But the basic idea is, what if you have data coming from, a collection of locations? Each location has its own mean and variance. You just get a couple of observations from each location. You want to aggregate all of the data together to learn the underlying distribution. So there's a lot of similarities between that and these MRA problems and signal processing. Okay, but I think in the interest of time, I'll skip that. And yeah, so we looked at a generalized MRA problem, which includes random translation, random dilation, and additive noise. It's challenging because of the perturbations and high frequencies. The more you know about the dilation distribution, the better you can do. And some of the future questions we're really interested in are, can we learn that dilation distribution? And can we sort of recast all of this in the context of distribution learning? And if the answers to those questions are yes, extending results to higher dimensions. Okay, so thank you very much. And I'll stop there. Take any questions if people have them.
Yeah, thank you very much. I know it's a very nice talk. Yes, if people do have questions, please do feel free to unmute yourselves and shout out or put them in the chat. I'll just stop the recording. Work out how to do that.